Alright, welcome back. This is P-Dog with the last of the Chapter 17 lectures, where we're calculating the heats of the reaction. So something you need to be keeping in mind, the question we're going to be answering this time is, what are two ways that you can determine the heat of reaction when it cannot be directly measured, when you can't just put it into a calorimeter and make it happen? Okay, and the first one we're going to use is Hess's law. So Hess's law is if you add thermochemical equations to give a final equation, you can sum the delta H's to give the total delta H final. This will allow you to determine the enthalpy indirectly. For example, carbon, in the form of a diamond, will decompose to form graphite. It takes millions of years, but it does eventually happen. So carbon as a diamond, and it's a solid, will decompose to carbon as graphite, okay, which is also a solid. Okay, so let's see how we're going to calculate this amount of energy. First thing we're going to do is we're going to write down the heats of combustion, because it's reacting with oxygen, of a diamond. And you can actually do this to a diamond. You can combust it, which also means burn, and it creates carbon dioxide when it's done completely. And when that happens, okay, and so not only does diamond decompose to carbon dioxide, but so does graphite. Graphite will also decompose to carbon dioxide. And it's also an exothermic reaction. However, we want diamond to turn into graphite. So we want diamond as a reactant. We want graphite as a product. But in this equation, graphite is a reactant. And so we need to switch it around and make carbon dioxide the reactant and graphite the product. And so we are going to switch that around. Carbon dioxide gas gets converted into solid carbon and gaseous O2 by adding heat for an endothermic reaction. Well, when we add these two together, we're going to get a final heat of reaction for the conversion of diamond to graphite. And this is going to be our diamond reaction, the same reaction from A, and except this time we're reversing B and we'll use C, and that is CO2 converts to graphite plus oxygen. Now, this oxygen is scratched out here because here it's a reactant and over here it's a product, and so they'll cancel with each other, 1 mole and 1 mole. Over here we have carbon dioxide scratched out and carbon dioxide scratched out because here it's a product and here it's a reactant, and 1 mole and 1 mole, so they'll cancel out with each other, leaving us with a diamond turning into graphite. Diamond is a reactant, graphite is a product, and a total delta H. If we add these two together, we're going to get a delta H of negative 1.9 kilojoules, which is what kind of reaction? It is exothermic, because delta H is negative. Okay, however, it's not very large for a process that takes millions of years. Okay, and this does bring us to our next kind of next way to tell whether or not the energy of something, and that is the heat of formation. Okay, and it's given by this symbol, this delta H sub F superscript 0. And this is the standard heat of formation, which is the heat that comes from forming a compound from its elements. And this is for reactions that occur at standard conditions. Okay, and standard conditions not to be confused with STP. It is not STP. These are standard conditions usually for chemical reactions that occur, chemical reactions that occur between solids and liquids, or just any time we're not trying to deal with a gas very much, or when one of our well, that complete. it's just a standard condition, and it's for 25 degrees Celsius in 1 atmosphere. So it's for all things that are reacting at that particular temperature, not just solids, liquids. So let me erase that. It's all things that can be reacting, whereas STP is strictly for gases and when we're trying to figure out molar volumes and that sort of thing. So our delta H0 is the heat of formation of our products, what we get, minus the heat of formation of our reactant. So in other words, once again, it's a big delta, which means it is final minus initial again, where products would be what you'd get, the final part, and the reactants would be what you start with. So for example, what is the heat of formation? What is the standard heat of reaction for the reaction of CO2 with O2 to form CO2? Well, we need to find the heats of formation of all three of these things. Well, because oxygen is already in its elemental form, elements do not have a heat of formation because they're in elemental form, and O2 is the elemental form of oxygen, so it's not going to have one. So it's over here at 0 kilojoules per mole. Carbon monoxide does have one. It's got carbon and oxygen, and to make it, it's going to release 110.5 kilojoules per mole. CO2 is going to be negative 393.5 kilojoules per mole. And the equation that governs this is 2 carbon monoxides plus 1 oxygen molecule will make 2 CO2s. Okay, so 2 moles of this plus 1 mole of that makes 2 moles of CO2. So our heats of formation is going to be 2 moles of carbon monoxide, but each mole requires 110.5 kilojoules to form. So the 2 times the 110.5 gives us 221.0 kilojoules. The heat of formation of carbon dioxide is 393.5 kilojoules per mole. We still have 2 moles of it because of that 2 right there. So we multiply this by 2 and we're going to get negative 787 kilojoules per mole. Okay, when we combine these in our reaction, because remember we want products minus our reactants. Here is our product minus our reactants. That's minus the negative. We're going to get, it becomes a positive. We add those together. That'll give us a total of negative 566 kilojoules. Okay, and this becomes an exothermic reaction because combustions always release heat, and that's a delta H of negative 566. And that's how we do it from the heats of formation. Am I going to have you calculate them? No, you will always have this data available to you when you do one of these problems. So that is it for standard heats of formation. There are more examples in your book, and you can always come up and ask me in class. So that's the end of chapter 17, and this is P-Dog signing off.